we've got an invader problem here that has hydroxide being mixed with, or rather lithium hydroxide being mixed with acetic acid. All right, so right away, I mean, I could just identify that we're dealing with lithium hydroxide, all right, is being added to a solution of acetic acid. There's our shorthand for acetic acid. All right, so we're going to take a look at first the invasion on what happens between that interaction, and then we'll analyze it for pH because it wants to know what is the pH of the solution. All right, another item that's given, of course, is the Ka of acetic acid is 1.8 E-5. All right, so this is all data from the problem. Now, when the strong base invades this weak acid, the only part of it that I care about is the hydroxide, which is going to be the determining characteristic of that strong base. All right, and there's no buffer or anything that it's being added to here. It's just being added to established acetic acid. So that's the only thing that it can choose to interact with. All right, I'm going to use a normal yield sign because we're analyzing a strong addition. So as we look at the Bronsted-Lowry here, we'll be able to see that a proton will be donated towards the base. So we're going to get some water. And now that that proton is gone, we'll be left with some acetate ion. In order for me to see who wins the invasion, we're going to have to do a mole comparison. All right, now the problem doesn't give me moles. It gives me a bunch of milliliters and molarity and stuff like that. All right, but we can figure it out over here on the side. For the hydroxide, I get a count of, I'm going to say 0.136 liters. I converted milliliters to liters there. And I want to multiply that by the molarity of 0.45. Now careful, there's only going to be a 2 sig fig answer here, and that's actually vital for this problem. But the 0.136 times 0.45 is 0.061. So there's my mole count of the hydroxide. All right, this was the OH minus information. All right, I need to find the mole count of the acetic acid as well. So I'm going to take the values that it gives me, which is going to be 0.129 liters, converted mils to liters, times 0.47 molar. All right, we're multiplying those together for the HAC. All right, and these multiply together again to 2 sig figs because you'll actually get different numbers here if you don't understand sig figs. But it turns out that to 2 sig figs, they're the exact same mole count. All right, water's not going to alter pH, and this solution did not have any acetate ion initially. So, of course, we need to subtract the smaller number for a limiting reactant comparison, but they're the same number, which is going to lead me to learn that there are 0 moles present of both of those reactants. However, this shift down is the shift up for my product. All right, so now in my beaker here, the only thing I have left floating around that affects pH is acetate ion. Now, this will send us down a hydrolysis road because we analyze acetate ion the way we would a salty solution. It doesn't fit the description of anything else. It can't be a buffer, right, because we don't have concentrations or amounts, rather, of the two parts. And it's not a weak or strong acid or base. So if we remember how hydrolysis works, we need to add the acetate to water in a rice table. However, right now we have moles, which is no good. We need molarity. So what I'm going to do is divide this mole count by liters, and it's going to be 0.265 liters. The way I got that was I added these 2 liter amounts together, right? Because we mixed this amount with that amount, and that will give me 265 milliliters. All right, so what I'm going to do is solve this for molarity, and you will get 0.23 molar. Give me 1 second. I just got a message I need to check. Anything to make the problem seem longer. Okay, good. So now that I have my molarity, I can go through with hydrolysis. So I am going to start a rice table that includes the addition of acetate ion to water. Now it's an equilibrium arrow, right? I can see that the water is going to act acidic here and is going to donate an H over to the acetate. All right, so that's going to form hydroxide and then acetic acid. My initial concentration of the acetic acid is 0.23 molar. All right. Water, of course, is not going to play a role. And initially in this analysis, we don't have any amounts of those guys, of the products. So let's shift towards the products. I plus C equals E. All right. So now we want to identify this X value because it will get us close to the pH that we're trying to find. Now, the Ka that it gives me is actually no good because it misaligns with the substance that's going to give me the X value. I need a Kb. So remember that Kb equals Kw divided by Ka. So I can say that Kw is 1 E negative 14 divided by the Ka of 1.8 E negative 5. And this is going to give me a Kb when you run that, get that quotient of 5.6 E negative 10. All right, so I've got a Kb value now that I can plug into an equilibrium expression, which of course will be my products over my reactants. So let's input that. All right, so my Kb is going to be 5.6 E negative 10. The products are X squared. The reactants, 0.23 minus X. I'll go ahead and cross-multiply this into a 0 equals expression, right? So the X squared will stay the same, but remember, when you cross-multiply this way, it initially starts everything on the opposite side of the equality. So to move it over, we just reverse the sign. So the times the negative X will turn into a positive value, so 5.6 E negative 10X. And then as I distribute to that positive, it'll be negative, which again is just doing the pre-algebra there. All right, and I get a value of 1.3 E negative 10. All right, which was just times the 0.23. This needs to go into your solver, which you've already been trained to do. And your solver on your calculator is going to spit out an X value of 1.1 E negative 5. All right. So remember, this X is this X, which represents the OH concentration at equilibrium. So that's what I have right now. We're trying to get to pH. So we have a strong concentration here, so I can take the negative log of that number, and it'll give me a pOH since we are analyzing hydroxide, and I get 4.96. All right. To get to my final answer of pH, I know these two values equal 14. Therefore, this must be 9 0.04.